I'm Roniel.
I'm DaRon.
And today, I have to be very frank here. We have a well thought out, well documented presentation on Ruby on Rails and how broken it is, right? And DaRon, I really want to ask, do you think Ruby on Rails is really broken? Like totally broken? Should they re-scrap this thing and just do something else?
So
Or why the hell did they come up with that anyway?
Why did they come up with it anyway? Did we really need yet another language?
I mean, we have too many of them. I think a lot of it is like they wanted to copy off of Python and then add a little Perl into there too. And then here you go, you have Ruby.
Yeah.
And it's not really a Ruby. Is it really a Ruby? Like, I don't really get that shiny figure from this.
It's also very slow.
Shiny. Yeah, that too. So why would anybody ever want to use it? That's the question. Why would you guys really want to use Ruby on Rails when it's really fucking slow? It's a copycat of a mixture of different shit, which is kind of glued together, and it's very vulnerable. Like, why would you want to use this shit? But however, we're going to talk a little bit more about that. I'm going to let DaRon actually kick this off, but we're going to talk a little bit more about how he particularly exploited something very trivial in Ruby on Rails. So let DaRon kick that off.
A little while ago, we had an engagement. So I've never actually had the opportunity to test a system that was using Ruby on Rails my whole career until just recently, because for the things that I work on, the things that I test, typically something this slow and inefficient would just in and of itself not be permissible. But I recently had an opportunity to do an engagement where they happened to be running Ruby on Rails, and they were using Ruby on Rails's protections as much as they could. For example, the cross-site request forgery tokens. And what we're actually going to discuss is how we broke the cross-site request forgery token scheme that they actually happen to use. And this was all in the course of a single engagement. And it didn't take long, actually. It was incredibly fast. So first and foremost, the thing that you have to understand is with proper cryptanalysis, as you know, Roniel, it tends to be very statistics and mathematically involved. So it's not like you're going to run it on just arbitrary things, right?
Yeah, do not just run it on any goddamn thing like somebody wants it. Some people want to test the entropy on things. Don't do that.
Right. That's exactly right. You have to understand in general what your goal is when you're doing anything with regard to cryptanalysis. And one of the most common mistakes is, just like what you were saying, people will sit there and they will try to determine the entropy on just random strings. Or let's say you have an OAuth token, and tied to that you have the token, you have the state, and maybe you even have a refresh token. And all you do is test the entropy on one of those three things, which is ludicrous given that the process for the actual entropy creation would be shared across them. They're all being created at approximately the same time. So you're actually going to get more from not looking between, say, the state tokens or what have you, but looking between the creation time spans. And that's actually something that we're going to go into in a little bit here. But what we wound up doing was, I was looking at this system. They had per page, per form cross-site request forgery tokens enabled. And when we were looking at it, we noticed first and foremost that there's this master token and it's sitting in a meta tag. The fact that there was a master token on each page that sits in the meta tag, and that they also had a meta tag that told you what the cross-site request forgery token happened to be, that indicated, at least to me, that there's probably something being done very fishy and very wrong here. That the different cross-site request forgery tokens, while they're claimed that they're per form and per page, probably aren't. And I said, okay, well, let's look more into this. Let's figure out what's actually going on. And we managed to find a page where they had a whole bunch of tokens. And all of these tokens were, because they had 5 different forms, so they had 5 different tokens plus the master token on a given page. And that made this much easier. The reason why it made it much easier was because, well, I could go through and generate a million billion tokens at once.
So wait, they had different tokens was this for just one user, but they had, or is it for multiple users?
This is for a given user. You would get a token. You'd have this master token so as you marched around, there's this master token, and that master token would change per page, but it doesn't change much. When you look at the base 64, for example, looking at this particular string here, I can just glance at the base 64 string, and I can tell you this is not, in fact, a random string. There are too many patterns just sitting in the base 64 string, and if you know the way base 64 works, particularly relative to 32, which is where this would have come from, taking them all as ints, you can very quickly see that because the successive bytes influence or are influenced by the preceding bytes, it makes it so that when we have this repetition inside of our base 64 string, we know I have repetitive characters buried in there.
Yeah, I see that. Okay.
The next thing that we also noticed that really told us there's something wrong is that we were able to replay tokens. And if it is in fact per page and per form, that should not happen. Every single one of these tokens should have been a one-time use, a fire and forget kind of deal. There is no way we could have and should have been able to do token replay on this if the per page and per form cross-site request forgery tokens were behaving as they should have, which is if, for example, they had a table, a state table, that is maintaining a list of all tokens, the associated users, and the associated actions or forms, as you would. That is how I would have imagined that they would be doing the perform tokens. But that very clearly wasn't what was happening because I could replay the token. We then also looked across, so first we were looking within an action, now we're looking across actions. And when we looked across actions, and we can see here, we have a post to settings user and a post to settings roles, so on and so forth, and they have the same, we're using the same exact token. So again, now we've just shown, look, these aren't one-time use, and they're not per form. The perform tokens themselves all seem tied to this master token. So we see at the top this master token, and then here are 4 sample perform tokens.
Oh my gosh.
Right. Yes. And you glance at this and you're going, wait, this does not, again, just glancing at it, this doesn't look random. There's nothing about this that looks random. In fact, they look all very closely tied together.
Mm-hmm.
Even not only do they look like they're closer related to the token, so when you compare them to that master token at top, but even when you compare them to one another, they just don't. And one of the keys here is, remember, since it's perform and this is a single page, and that page, when you hit it, generates all of these tokens, I'm able to see most likely each one of these tokens being generated sequentially with no other token being created in between. And what I mean by that is, if I'm even hitting a heavily used system, it's unlikely that another process preempted mine during at least the generation of 2 or 3 of these tokens. So there's a high and generated tokens of their own. So there's a high probability that when it's pulling from devu random or wherever it's getting its entropy from, it's getting them now in a block. So I'm better able, as a result, to actually look at the algorithm and see, where is my failure? And how predictable is this? And can I actually guess these and guess them right?
So if you're able to guess them and actually what you are and predict them, then you could pretty much use any one of those tokens to just forge whatever you wanted, right? Um, because you're able to replay or or guess them or predict them, and then I could just pop in one that I guessed and then forge whatever request. So it doesn't make it protected anymore.
Exactly. And so now here's the key, because normally the way this would work is you might go through and you might say, okay, but DaRon, the problem is in order to do your attack, you have to already have tokens. And the answer to that would be yes, but I don't need your tokens.
Yeah, because you can predict it. You can get your own.
That's exactly right. I can generate your tokens. All I need to do is get, first and foremost, I need to do the cryptanalysis. And if the algorithm is what is broken, then I can do the cryptanalysis on my own machine, discover a function that best approximates how this thing happens to be picking its values, and then I can get just one token of yours and generate all other tokens from there using this function. That, by the way, is exactly what we did. So we're able to break the algorithm without knowing what the hell we're writing, without knowing what the hell this thing is actually doing, and we'll get to how we do that. All right, so here's the cryptanalysis. The first thing that we wound up having to do, of course, was harvest tokens. Now, remember I said we found a page that would pump out a lot of tokens. Now, interestingly enough, this system also told us which server happened to be servicing it, because they had a header value that included the server name. It also included what region they're in and what access zone they're in. So we were actually able to amass a lot of data, and this is actually really good because this thing was a load balance system. There were 4 servers on the back end, and one of the things that you really have to ask yourself when you do this kind of analysis is, where is the problem? And because we're able to actually differentiate and say, okay, well, here are all the tokens tied to this server, here are the tokens tied to this server, and of course within that, here are all the tokens from this request, this request, this request, this request. We can run both intra and inter-server analysis on these. And that is going to tell us, maybe is the problem with entropy collection is this guessable only on a per server basis? Is the problem with the underlying algorithm? What is going on here? All right. So we generated a whole bunch of tokens, just a massive amount of tokens. It took approximately 5 minutes to grab all of our tokens. And we were able to actually do analysis first on that intra-server. So this is looking all the tokens that server 1 creates, and we can do different statistical modeling. We do z-score, we do Pearson, we do chi-squared, we do Spearman.
Now, not to cut you off, but before we go into even that, are you able to explain a little bit on what the Pearsons and the Z-score, what's the difference between them and how they actually are used for people who don't know?
Yes. So what Pearson winds up giving us is a linear relationship. Is there a linear relationship between these? So what we're trying to do is, again, we want to figure out what function best approximates all the values that we're seeing. Because if I can get a function that well approximates what we're seeing, then I can use that function to map out values in the future. And some of these functions will give you, say, a linear relationship. Some will give you a quadratic, some will give you parabolic. So I want to try to figure out what shape is this data. But it also will give us relationship between, in this case, we're doing byte level analysis. So do we have a 1-for-1 on these bytes? Meaning, does the value of byte 0 directly impact the value of byte 31, for example? And now what we wind up doing is with, say, the chi-squared, we can start to analyze, well, what's the probability of us seeing this value, this byte value, this many times, or at this general location? That probability tells us, hey, we're seeing this too frequently, but we're also not seeing this other value over here frequently enough. Let's say, for example, you were talking about flipping a coin.
Yep.
So that chi-squared analysis is going to tell us, let's say you got 1 sequentially, 32 out of the 100 times. 32, a 1 being heads. So heads 32 times in a row is statistically incredibly unlikely. So if we're talking now cryptanalysis in ciphertext, if it's truly random, I shouldn't keep seeing that same number sequentially. And that's what that chi-square analysis is going to give you. But what it won't give you is a function that fits it. All it tells you is we have a problem. And because we have a failure effectively in entropy, this thing is appearing too often, or it's not appearing often enough. That's a problem. Whereas Pearson is going to tell us, hey, these values are actually directly dependent on one another. And there's a linear relationship that describes it. And then what you do after that is you map it out. And then, of course, using good old-fashioned calculus, you find a function that approximates that. But the beautiful thing is, if Pearson is telling you, hey, there's a problem, then you know it's going to be linear. So it's going to be a very simple function as these things work, or, go.
So I have 2 questions. Can you predict, since you can predict these things in the future, can you also predict the values in the past?
Yes. See, because that function is actually going to, of course, the way you would do it is your root counts as the 0th time. For, let's to give an example, say that we looked at this first value that we see here, this hidden name, authenticity token, W5, so on and so forth. So let's say we make that our root. Anything created before that would be -x and -y. Anything created after that would be +x, where x is our time, and probably +y, although, of course, I guess both could be positive or -y. But if x is your time, then that will approximate where it is, and that time can be physical time, because it might be on a clock. And that's one of the other things you have to figure out is, okay, well, is this time-based, or is this based on just requests? Meaning that time could be request 1, request 2, request 3, or it could be clock time 1, clock time 2, clock time 3. And what clock time is can be a number of things. It depends on how they're associating it. They may be binding it to seconds. They may be binding it to minutes. They may be binding it to the Linux timestamp, or I should say to the Unix timestamps, what have you. But just understand that X is time. The units of time we don't know, and we'll figure it out as we go, kind of deal. Does that make sense?
Yep. So the next question is looking at this, looking at this graph or looking at the chart. Let's just say, for instance, you have 90 degrees here, right? The x-axis versus the y-axis, when you look at that one in the middle, that line is going down, is that where you actually see the comparisons at, besides where it meets from 0 to 62? Like, I'm assuming that the line that is pointing from 30 to 32, is that where you do the comparisons? Or is that not where it's being compared at, in that line that's going linear?
So what that line is actually telling us is that we have a relatively strong byte level dependency. And what it's telling us is that byte 0 heavily influences the value of byte 32.
Okay. All
Byte
right.
1, so on and so forth. So our goal then is to figure out exactly how strong that relationship is. And we actually shouldn't see a line like this.
Okay.
I want to point out that you can see a very clear line is bad. And to what you're asking, so when we look at this, if it's up here, that means that we have a positive relationship. If it's down here, that means that we have a negative or an inverse relationship. A good example of that being, let's say the value of uh, byte 0 is 0. That'd be a terrible example. 1, 1, 1, 1, 1. All ones. Then the analysis would show that the next one would be all zeros. For example, the one that's tied to it would be all zeros potentially. Okay. That just shows, hey, this is a direct inverse of that one. That's all that it's saying. So Pearson, again, is telling us we have a linear relationship. The next one we see is this Kendall, and you'll notice the relationship isn't as strong. So this just reinforces that we have a linear relationship as compared to a parabolic, quadratic, or so on and so forth relationship. But we do see Spearman is actually fairly close to the Pearson. Right.
I was just going to say, because the Kendall one, if I'm saying that right, Kendall?
Yeah.
You can see where it's breaking. It's not like it's very straight, but the Spearman and the Pearson one seems very related.
Right. And that's mildly abnormal, but the important thing really here is that the Pearson is telling us we have a linear relationship between these bytes. It's a little fuzzy at some points, and we'll get more into it, but the thing that you have to ask yourself at that point is, all right, so we've verified what we said was right. When we said, look, if you just glance at it, it doesn't look random. This tells us it's not random. It's not even close to being random. It also tells us it should be obvious that it's not random because it is a linear function. And linear functions aren't complicated. It's not like you have, this isn't a sponge function or something crazy where you would expect a wonky quadratic or some other thing. So whatever's going on here is really, really, really bad.
So if it was random, then they would probably be all over the place, right?
Yes, your map would be a lot of this. I don't see color right, so I'm going to say gray.
Okay. Yeah.
I don't know what it is to you. It'd be a lot of white and gray.
This looks more tannish to me.
Okay, a lot of white and tan. Thank you.
Okay. Yeah. No, it's okay. Okay. One more question here. Just going on this. This is kind of like, you probably don't want to tell everybody your secret, but when you're doing these graphs, are you using your similar statistical graphs that most people use with Python? Even though I know you hate Python, like the mat, that mat or graph thing that they use, or are you using like your own? Like, is there something you particularly use, like Java? Like, if somebody wanted to do this and to make their own graphs, would you recommend them using the pie graphs, or do you use something in particularly different? Because I would use the pie graphs here to do that if I was actually calculating. That's how we did it in our statistics. We were doing statistics in school, but
there
just
are.
Wondering.
Sorry.
No, go ahead. I was just wondering your preference.
The truth is, I usually will use something like C when I'm doing cryptanalysis, or C++, only because the amount of data I typically have to chug, and because the analysis itself, if you were to use Java's not as heavy as it used to be, but it's still a little heavy. Python is really heavy. If you have short strings and you don't have a ton of them, sure, you can use Python. They have libraries that are specifically dedicated to these three. I don't remember the name of it, but we can put it in the description below. The And they will produce graphs that look identical to this. These are very standard graphs that you see here. So they definitely have Python stuff that can do it, but I usually use C or C++.
Okay, I just wanted to for anybody out there that didn't know how they can do these, because I'm sure people are going to want to. We're not going to give it to you, but however, a fun little project would be if you're doing some cryptanalysis. Maybe try to write your own. We'll put some of the things down in the description, but it's just to give some people some insight on how they could probably do this if they wanted to do their own and not use the Burp Suite sequencer. That's what
Which
everybody
doesn't work.
No, it doesn't. I am one to say it does not really work at all. So that's why I found this very interesting, and just wondering, because I would use the pie graph. I'm used to using those to actually easily put up a graph and show how they are linear or compare them. But sequencer does not do a great job. And if you don't, they only I think they only allow you to have I think it's 20,000, maybe less. And I think in this particular case, how much data or tokens did you need to get in order to do a real good analysis?
I took over 60,000 and then I took another 50,000 later on because and we'll get to why, but I wound up doing different time slices. So this first analysis was relatively plain Jane. You all remember, of course, the harvesting token script is fairly basic. And because of the way I did it, it was sequential, and that's why it took as long as it did, which meant that your tokens were a little more spaced out. What I then did was I did some multi-threaded runs where I was doing 10 plus threads and grabbing a lot. And I did that, and we'll see why, but to do that time-based comparison to say, okay, well, can we figure out what n is? So what is that unit of time? Is that unit of time in ticks? Is that unit of time in calls? What does it happen to be? Because that's important. And so I took approximately 110,000 tokens in the end. And yeah, you could not do this in Burp Suite. Even something as obvious as this one, it's too large. It's 512 bits.
I think they only allow you to do like 20,000 or something like that. I think it's not, you can't go further than that.
Right. Yes. And 20,000 tokens isn't enough to properly analyze something this long unless it were incredibly broken, like ridiculously broken. And this is very broken, but it's not that broken.
No. Yeah, that makes sense.
The other thing is it only gives you chi-square analysis, and chi-square analysis only tells you that there's something wrong. It doesn't tell you what's wrong. It doesn't give you enough data, and it certainly won't let you predict values in data.
Yeah, that's where it sucks at. It's hard. To me, it always found it hard to try to predict especially if you're trying to say, for instance, we're not even looking at the tokens here, but we're looking at the session, tokens and stuff like that. And you're trying to see if they're predictable. Like that does a horrible job of trying to tell you whether it's linear or, how they correlate with each other.
Right. That's exactly right. So this, of course, is Intra-Server, but this is only server 1. So our question then is, do we see the same relationship in server 2, 3, and 4? Because maybe the problem is an entropy problem on server 1. Meaning, maybe server 1, it could be that they aren't pulling from dev-urandom or some other secure random source. It could be that server 1 was just seeded with a bad seed. That's certainly possible. It could be some other entropy-based issue, or maybe the moon and the stars just happened to align, and when it was chaining that IV, because the IV just moves across as you go through, when it was chaining the IV, it got wounded, what have you. There are a lot of things that could happen. So let's look and we'll see, what do we see across server 2? And you notice I just switched, and do you see a difference in the graphs?
They're the same.
They're the same.
Yeah.
And here's
Sorry, I was just taking a look at that.
yeah, no, that's fine. Here's all 4 of them, just marching down all 4 of them.
Yeah. That
So
sucks.
yeah, this is a big issue. Now you're still left with the question, right? So these are 4 servers. They're load balanced. Are they are they clones from the same instance? That's very common. You have a template server, you basically suspend or save that template server, and then you bring it back to life for each of these instances. If all of these instances were turned on at the same time, and the clock, that x-axis, the unit n, is time-based, then a bad seed in one would be a bad seed in all. In fact, any seed in one, if they would have the same entropy across them. Alternatively, if it's request based, it's possible this thing was not doing round robin load balancing. It actually was random load balancing. It wasn't even load based load balancing. So it seemed unlikely, very unlikely, that that's the issue. And there's a much bigger problem. So looking at this again, we see the Spearman and Pearson they're not the same, but they're pretty damn close. Pearson's a little stronger. That's good. That makes our life easier. So let's take a peek at Interserver. So now instead of looking at a server by server basis, let's look at all these tokens across the Interserver. And you'll notice we see the same general relationship, but it's a little lighter. It's a little lighter. It's not as strong. So that's good-ish. That means that the issue could be, whatever this issue is, it's shared. It also means that it's probably not an entropy issue. It also means that we should look at one more big thing after, of course, we note that, again, Pearson and Spearman continued to be really close, right?
Mm-hmm.
So let's look at the forms, because we were just looking at the actual, just at the per form token. So we're ignoring the master completely, because maybe the master is what's throwing us off. We know that the master and the form tokens are related, but it could be that while they have a relation, the per forms are built off the master, and that's throwing our data off. So looking just at the form tokens, and this is across the servers, we see still that relationship is present. What we're going to look at is the forms across time. So remember, I said, I then went through and I said, okay, well, does time matter? And when I did this, I did a very slow grabbing of tokens that took about 30 minutes on top of the other one. And I grabbed fewer tokens. So it was 30 minutes in order to grab, I believe I grabbed roughly 15. And then I did a quick burst where it was a ton of them. And let's see what this winds up looking like over each of these time slices. So this is slow. And we notice that relationship is actually really fuzzy. You see a lot more holes, right?
Yep.
This was fast.
Wow. Wow. And even Kendall was coming close.
Even Kendall was coming close. It's right. So what this tells us is, I mean, look at that. This is the byte level. We're not, the byte level. We're not even at the bit level yet. Byte level. I would expect that the byte level just tells you that there's a problem. It's the bit level that's going to tell you exactly how everything goes. Because with the byte level comparison, if bit 0 has a negative correlation, but bit 1 has a positive correlation when compared to their respective byte pairing, that's going to throw off the bit level analysis. That's why these aren't ones. That's why they're all, well, not all. Some of these actually are ones. It's why these are less than 1 and -1. They sit in that in between, where a lot of them were more like 80, 90, 98, things of that nature. So let's look at just the masters. And when all you do is compare the masters against each other, again, I mean, this is as strong as when we ran it fast. So we have a critical problem here. We have an incredibly critical problem here because I can guess the master token and I can derive the per page and per form tokens based on the master.
So it was the master, just to go back, just in case I missed it or anybody, was the master always, the master wasn't always the same? Was it give you a
No,
different?
the master is not always the same. It's different.
Okay. All right. Just wanted to make sure. That makes sense. Wow. Yeah. And if you're predicting, if you're able to predict the masters, then you can, I mean, you have control of all of that.
Exactly. That's exactly right. And you'll notice what this graph is actually showing us is it's a complete foldover. So literally, I take the first 32 bytes, and I fold the next 32 right on top. Right on top. That is what this is showing us. That's exactly what this graph is showing us. So it is incredibly broken. If I guess the first half, I can guess the second half.
Wow.
All right. So looking at this, rather than stare at a graph, because, graphs can be, they're small, let's just take a peek. And we can see here, we've got these byte pairing. So byte 0 is 0.91. Its correlation coefficient is 0.91 to byte 32, meaning they're almost a 1-for-1. It's almost complete. 1 to byte 33 is negative 0.9, which means it's an inverse relationship. 2 to 34 is almost negative 1. So it is also an inverse. These are all strong. All of these are extremely high correlation coefficients. All of these tells us that the strength, that these byte pairings are real byte pairings. This is not a joke. This isn't random. This is an incredibly big problem, and we can see how it just walks right down that line. And you'll notice we see the same thing with the left, of course, those are our per form tokens. The right are our master tokens. And you see again that foldover, right?
Yeah. Wow.
We can see here that both on the per form and on the master level, we have incredibly strong correlation coefficients. We can see here that we even have ones and negative ones on the master. So we know for a fact that byte 0 is tied to byte 32, that byte 1 is tied to byte 33, that byte 2 is tied to byte 34, that byte 3 is tied to byte 35, so on and so forth. We know these things for a fact. So the next question, and when we know that we can find a linear function that actually maps this, and that using these linear functions, then we can go through and accurately predict it. We also know that time matters. So we know that on the x-axis, time is our factor. So the next thing that we do, it's called chi-square bit run analysis. Now, this is something that Burp Suite can do, but it doesn't do it very well. Again, the tools, the stuff that I've created for myself, it will handle all of this, and it does it very nicely. I know the Python libraries and their Java libraries, Python and Java statistical libraries that will give you this data as well. And they do a phenomenal job.
So what do you take this? So it's just for instance, this is the form token. So you take all your form tokens and then you run it to, just for instance, if I was using Python, I would run it to that analysis or using that library, and it would give me an analysis particularly like this that would correlate all of them. Is that similar, like something to what you're saying?
Right.
That you could do?
Yes, and it'll give you the chi-square. So when we do the chi-square for a bit run, and you see the graphic on the top right, those are bit runs. You'll notice we have highlighted where you have zeros, a 0 next to another 0. That is a bit run. And a 1 next to a 1, that's a bit run. So bit runs go within the token. So when I look at your token and I turn your token into a bunch of bits, what we're looking at is, okay, how many ones do we have next to each other? How many zeros do we have next to each other? Starting at each bit. So starting at bit 31, for example, what is our bit run? And we do a chi-square analysis based on that bit run. What is the probability that we get 0, 0? And that we get it X times, etc., etc. That's what we're doing here. And you can see here that very clearly we have long bit runs. We have bit runs that don't belong. And that the chi-square analysis, because we do it not only based on where it's 0, 0, it can also be 0, 1. What's the probability that I see a 0 and a 1 next to each other from this bit onward? What's the probability that I see the string 0, 1, 0, 0, 1? And for something like this, that's what you effectively do is you feed in a list of all values. So if I take the byte, the whole byte, and I break it down into bits, I know how many different combinations there are. And I can calculate the likelihood that I see that combination in a random sampling n times. And that's what chi-square analysis is really doing is, am I seeing combinations excessively? Am I seeing things that I shouldn't be seeing too often or not often enough, as the case may be? That's what we're looking at here. And we can see that we have these very lengthy bit runs where there's no way this value is random. It's not going to happen, not in the real world.
Because if you look over the random sample, like there's a lot of similarities.
Right. Yes, that's exactly right. That is exactly right. So the next thing we can look at is what's called the longest run. So the longest run is where you take these tokens and you turn them into bits and you stack them on top of one another. And now we can see across each row is a token. So looking across this, when we have a longest run, that's where you have tokens where they have in sequence. So this is token 1, token 2, token 3. And on that right side, we have at the third position, keep in mind we're computer scientists, so we start at 0. At the third position, we have the bit run 0, 0, 0, 0. That's our longest run in this particular sample. And that's of 4 tokens. We see this bit go across 4 separate tokens. We don't want to see that. And you'll see we have bit 508 whose value was the same exact value across 2,844 tokens. Sequentially done tokens. Yes.
That's crazy.
Right. And when we do, now you may ask, well, again, why did we do byte level analysis first? And the real answer is because bit level analysis takes a lot longer. There are 512 bits. It's a lot of bits. There were only 64 bytes. Right. Yes. And given how many tokens we had, that would take a long time, and it did take a long time to crunch through all of that. It took, I think, 3 hours. Whereas the byte level literally was returning within 20 seconds. So I can get that quick smell test, and it worked very well. And if it hadn't, then maybe you start resorting to bit level. But that's why we started at that byte level rather than the bit level. It's also why, again, we started at the visual level. And visually, it didn't pass the smell test, so to speak. Visually, we saw there's a problem. So what's our takeaway? The takeaway is that Ruby on Rails' anti-cross-site request forgery token system is actually broken. In fact, I know how it's broken, and I know why it's broken. They're not generating it the way that people think they are. The basis for it is there's a system level property that they pull from, and they're using weak hashing algorithms. And this combination of this static system level property is why we saw what we saw across the servers. That they're using a weak hashing algorithm, and they do in fact base the second half on the first half. And they do in fact base the performs on the master. But we knew all of this just from our analysis, and we created a function so that I still to this day, I don't know what their values were. And I don't need to know what their values were. This is a beautiful thing. Cryptanalysis can have different goals. In one goal, you're trying to figure out what the key is that they're using to encrypt data. In another goal, I don't care. And with these tokens, I don't need to know what the actual plain text for the ciphertext is. I don't need to know what the ciphertext means. I don't care what the ciphertext means. It's immaterial to me because I'm not going after the plain text. I'm going after, can I guess this in the future? And we found out that, so not only are these things reused within a session, but if I capture a master token, I can guess all perform tokens. In fact, I can generate all perform tokens. Or I could just send the master token itself. That was the weirdest thing, is the forms all accepted the master token. So there was no point in the perform tokens.
Wow, they really pull from you random and they use weak hashing.
Yes.
That means anybody that's using Ruby on Rails right now is vulnerable to this attack.
Yes. And this, by the way, it's been the case at least since they implemented perform tokens. I didn't look further back than that, but honestly, it's probably been this way since their cross-site request forgery protections were created when they first added it. I know that was before version 6, but version 6 and above, 100% easily guessable cross-site request forgery tokens. I can do it in my sleep.
Woo! Wow.
Yeah.
This is bad.
Yes. So there's another really important takeaway from this. And that is creating millions and millions of tokens isn't actually a good thing. They did the perform thing because the claim was, okay, if I make it perform, then you can't just send me any old token. So we're a little more secure. But the problem was, by creating perform tokens, they made it significantly easier for us to do cryptanalysis and figure out that this is broken. All I needed was a page. I didn't even need this, but it was beneficial that I found a page that happened to have a lot of these tokens. The more ciphertext you create, the more obvious the flaws are.
This is interesting because this is a different way to actually do cross-site request forgery than most people actually do. A lot of them are the most common ways I see besides the regular way, but once they have analysis, they look to see if it's actually in the headers or stuff like that, or in the forward requests to actually see if they could forward it. But a lot of people don't actually talk about actually guessing these. And by the way, I want to say that I think this issue is in other thing like frameworks besides Ruby on Rails as well.
Yes.
Once you said this, it kind of reminded me of something else. I can't remember what it was. I don't think it was a PHP one, but I think it was some other application that did the same thing. But this is interesting to me. I've seen this multiple times in other areas. So, yeah, it's not just Ruby on Rails. It could probably be any other framework. So if you see this, you might want to actually do it. But again, it's best to know what the hell you are doing and not just actually go up and say, oh, I'm going to test this entropy. I'm going to test that one. Like, a lot of people want to look cool, do these things, but don't really know what the hell they're doing. But I can guarantee you it's in a lot of different frameworks out here besides Ruby on Rails, as DaRon just said. So this is pretty cool.
Yeah, it was honestly a lot of fun. It really didn't take very long. In fact, actually, the longest thing was writing up the cryptanalysis. That took longer than performing the cryptanalysis. It took about a day to write up the paper. So,
with that being said, this is a lot of statistic analysis here mixed with some calculus. So, uh, if you're not good at statistics or calculus, you probably won't be good at this at all. However, doesn't mean that there are not libraries out there to help you. So, if you kind of need to, you want to write up your own thing, I think it should be simple to do it. But again, this will probably help you understand how to do that.
right.
But I guess the challenging part is actually understanding the correlations between them.
Right.
How to do the byte level analysis versus the bit level, level analysis, which they should be not too bad if you have the libraries, but it's all depending on how you actually compare them and how they generate. But I think some of these libraries, Python, is not as good as whatever you're using. But and then the graphs are not as good as the graphs you're using as well. So say that. But I guess either way, this will give you some idea of how to do that. And I guess the biggest challenge would be actually writing a cryptanalysis report and explaining the issues. So
yes, because you have to explain it so that the people can understand it. And I think to what you're saying, that was the hardest part. Was when I first found this, I of course immediately notified them, and this was critical because it let us circumvent, by and large, all their cross-site request forgery protections, because it goes across users. So it's not even within a given user. If I go through and hit your login page or something on your site that has a token as an unauthenticated user, now I can generate all the tokens for end time and just pump them out like mad. It's incredibly easy to do after that. And all I needed was one, because I already had the function that would let me tell me what the next values would be. And what that ultimately wound up meaning was, when they saw it, I had in the notification that additional data could be made available on request, and they started looking into it, and they're like, we're pulling from devu random. I don't understand what's going on. Can you give us the cryptanalysis? And so I did, and it was detailed. It was like 6 or 8 pages or something like that of a lot of data, and that was on top of what was already made available to them, which was a significant amount of data. I'm sure you remember.
Yep, it was a lot. Oh man. With that being said, it reminds me that you can use the same the Spearman and Pearson and Kendall and these type of things towards other things as well, like predicting object identifiers, session tokens, and these things as well. But it made me think about when I was doing one project that I told you I could predict because of MongoDB. The way they were doing it was predictable, but you could guess the past and the future.
Right.
But actually having a chart would have been even better to actually describe. I think they understood what the issues were. I had a script that I used, but I do think that it would probably been even cooler to be able to show the graphs and why and how they correlate and why they were issues, and not just showing that I could enumerate and get all of these values.
And the chart is even more useful than that table. You remember the table where I had all the bytes? I mean, that's a lot of numbers, right? The chart, it's
the chart is like I said. Once you kind of go through and explain it, it makes sense. But the table, the chart's just kind of literally, if you're like myself who likes to really see pictures, that kind of explained everything for me. For me, I didn't even need to see the table. It was like, okay, there's obviously a problem, but for more people who want to get more of a breakdown on how many, like how long or how many times it was seen in a particular, byte or whatever, that might have been very interesting for people, especially if you're very analytical. But for me, just seeing the chart, I was like, yeah, these really seem to be the same all the way across. However, the two, as we know, this Spearman and Pearson were very close related. They were very related together. So now that I think of it, charts really bring out a lot of details when you're thinking about showing how something is predictable and how they correlate with each other. So it brings me back to my statistical days when we had to make charts for everything and show how they related to each other. So even drawing the chart. we didn't have the opportunity to do this in Python until later on into part two of the course. But the first part of the course, you had to draw the chart and make them and show how they would correlate with each other using math. So that's interesting. But again, this just giving everybody details. This is you can do it not only on surf tokens or stuff like that. You can do it on a lot of things, but you just need to know what you're doing. So
right, yes, it's similar to what we did for the ASCCB, actually.
Mm-hmm. And if you haven't, you guys should definitely go over and check that. Literally, boost those views up. We're giving you some really good content here, and we really would like to get more people to subscribe to the channel and look at some of this stuff because a lot of stuff that you're not going to see out there. I guarantee you're not going to see none of this shit out there. And that is one of the biggest problems is that most people don't believe a lot of these things or can't believe this shit could be done because what you see online they're only giving you what their experiences of what they had during that time period, and it's not like they're updating the information with new things that are being done. Everything is always constantly changing. So here they're getting things that we're seeing like live, and that you won't see anywhere else. So definitely hit that like and subscribe button, and yeah, get the views up. Come on now. This has been our segment. I'm Roniel.
I'm DaRon.
And again, like, comment, subscribe for more stuff like this or episodes like this. Until the next time.
Have fun.